What's up, guys? Another video on structure and bonding. This time looking at the intermolecular forces between simple molecules. So if you've not checked out the previous video, make sure you do that. We need to know about electronegativity first. If you have done, let's carry on. So for starters, let's think about the strength of these bonds. So we've got covalent, which is obviously an intramolecular bonds. So bonds within molecules, and then these three are our intermolecular forces, so bonds between molecules, right? So what we're talking about here are the bonds between molecules. And covalent bonding much stronger than these. Hydrogen bonding is the strongest, dipole-dipole next, van der Waals next. And we'll sort of explore these in turn, starting oddly enough with dipole-dipole. So this is very much what we spoke about last time, right? Where chlorine is more electronegative than hydrogen, and so it draws that pair of electrons closer towards it. So what we have here is, because we've got sort of more electrons than we might expect around this atom, we've got a very slight delta negative charge. And because we've got slightly less electrons than we might expect around this nucleus, we've got a slightly delta positive charge. And, you know, it doesn't need me to tell you that like charges will repel and opposite charges will attract. And that's what we get here. So each one of these is a HCl molecule, right? So because of this delta positive and delta negative bit, probably the other way around really, chloride is obviously going to be much bigger, so delta negative, delta positive, we get this attraction. So we call this Cl and this H. We get this attraction. This is our dipole-dipole attraction. Called dipole, di meaning two, pole meaning poles, much like we have the north and south pole. So we've got this negative end and positive ends. This is a weak attraction, but it is an attraction. And so there's going to be a slightly higher melting and boiling point than it would be if these dipole-dipole attractions weren't there. Then we go to a very special type of dipole-dipole, and that's hydrogen bonding. So I've got water as an example here. All right, we know oxygen is going to be delta negative. The hydrogens are going to be delta positive. And this is very special in that, you know, we have these lone pairs because there's such a big difference in electronegativity, and because we have these lone pairs, we get much stronger dipole-dipoles called hydrogen bonds. And this is only ever going to be the case when we have, obviously, hydrogen bonded to three choices. And that's going to be oxygen, nitrogen, or fluorine. So hydrogen bonding will only ever occur with these. And it's worth quickly showing water is a bit of an exception here in that it forms two hydrogen bonds per molecule. If we took something like ammonia, say, so if we've got NH3, we've only got one lone pair. Oddly enough, that's only going to form one set of hydrogen bonds per atom. And obviously there'd be another hydrogen bond here and then up there, but this would only have one other attracted towards it. And hence why water has got such a high melting and boiling point compared to things like ammonia, which are gases at room temperature. And last is van der Waals. So van der Waals is when we have no difference in electronegativity, right? So we've got our molecule and there's no difference here. And this is what happens, right? So try and think of this as more just where the electrons are. So we start with our non-polar molecule. And so, you know, whatever atoms are inside this, so say if it looked like this, there are no difference in electronegativity, and so the electrons are sort of shared equally between them. So you've got this solid cloud. But, you know, if we took a little snapshot in time, it wouldn't necessarily look like that, because electrons are constantly moving. And so over time, they're sort of moving over to here and over to here, and they're fluctuating. And they're fluctuating like this, right? So a certain snapshot in time, we've got more electrons this side, we've got more electrons this side, we've got this constant sort of wave, if you like, this wave of electrons. So electrons are constantly moving. And we get something here where they're next to other molecules. Is now all of a sudden what's going to happen? This electron density is going to repel electrons in a molecule next to it. So it's going to start to induce a dipole. Until we start to get something like this. We start to get these weak interactions, and these are far weaker, between molecules, because the electrons have moved and shifted, and during the second where they are shifted, they start to induce charge, and we start to see very weak intermolecular forces form. So these are our van der Waals forces here. Worth mentioning here, so this is again only with non-polar molecules. And worth mentioning again, well, I say it's only with non-polar, it's going to be with all molecules, but the polar molecules are also going to experience hydrogen bonding and dipole-dipole. So technically it's with all molecules. And worth us knowing as well, the bigger the molecule, means more electrons, means more van der Waals. And again, it is with all molecules, but if our molecules are polar, they're going to be undergoing dipole-dipole or hydrogen bonding as well. So let's try and put this into context. So what is the order of melting point for the following? We need to justify that. So we've got HCl, we've got HF, and we've got H2. So straight away we know with H2 we've got the same atom, and so there's going to be no dipole attractions at all. So this is just van der Waals. With HCl, we know we're going to have a decent difference between hydrogen and chlorine, so we're definitely going to get some dipole-dipole. And van der Waals. And lastly, HF. Remember the fluorine, it fits in with our pattern here. So we've got fluorine, nitrogen or oxygen bonded to hydrogen, and then we get our special type of dipole-dipole, hydrogen bonding. So here we have hydrogen bonding and van der Waals. So hopefully there, the highest to lowest, we're going to have HCl as the HF, as the highest. We're going to have HCl in the middle, and we're going to have H2, sorry, as the lowest. And here we can say strongest intermolecular forces, therefore more energy to overcome forces. And we just do the opposite here, right? Weakest intermolecular forces only, therefore less energy required to overcome the forces. Question I want you to give a go is this one. It's a little bit more complicated, but the melting point of XeF4, so this has come up again, higher than the melting point of PF3. Explain why the melting points of these two compounds are different. Give the shape again. Explain why each molecule has that shape and how the shape influences the forces that affect the melting points. So again, if you're not sure how to answer this, look at the last video, the video before that, all of our videos on intermolecular forces. I'll put a link up here. Give that a go. I'll answer that at the end of next video. For now, let's answer the question that we had at the end of last one. So here, again, this will be familiar. So what we're looking for is, first of all, do we have polar bonds? Yes, we know we've got a big difference between carbon and fluorine. So we've got delta positive, and our fluorines are most electronegative, a delta negative. But have we got a polar molecule? No, because we have our layers of symmetry. Tetrahedral, if all of our R groups are the same, we're not going to see a polar molecule, right? So not a polar molecule. So as symmetrical. And of course, all we'd have to do is swap one of these F's for an H, and all of a sudden it is going to be a polar molecule. So not much needs to change in order for that to change, right? Next, XeF4. Again, fluorine are most, so delta negative, delta negative, delta negative. But again, the same thing. We're square planar, so we are symmetrical. So again, not a polar molecule as symmetrical. And hopefully after watching the last video, this video, sorry, you'll know that therefore we're only going to see van der Waals forces in both of these. I hope that helps. Give the questions a go. Let me know if there are any questions in the comments, and I'll be happy to answer them. Otherwise, see you next time, and happy revising until then.